Deep in the heart of a ship's engine room, there's a constant conversation happening. Countless instruments are talking to the control room, sending vital information about the ship's health. Today, we're going to decode one of the most important languages they speak, the 4 to 20 milliamp signal.
Okay, let's dive right in with the central riddle, the one that stumps a lot of people at first. If a freshwater tank is completely empty, bone dry, 0%, why does the sensor send a signal of 4 milliamps instead of 0? It seems totally backward, right? Well, there's a genius reason behind it, and that's exactly what we're going to unpack.
But before we can solve that riddle, we first need to understand what this signal language even is. Why is it the gold standard for the incredibly tough, noisy environment of a ship's engine room?
So what is it? Put simply, the 4 to 20 milliamp signal is basically a universal language for industrial gear. It's how things like a tank-level sensor can talk to a control panel. It translates a physical measurement, like how much water is in the tank, into a very small, very precise electrical current.
But that kind of begs the question, right? Why use current? Wouldn't sending a voltage signal be more straightforward? Well, when you're on a ship, maybe miles out at sea, reliability isn't just a nice-to-have, it's everything. And that's where this choice of signal becomes absolutely critical.
Just try to picture a ship's engine room for a second. It is an incredibly noisy place, and I mean electrically noisy. You've got massive pumps, generators, all sorts of machinery creating interference. A voltage signal is kind of like a quiet whisper in a really loud room. It gets distorted easily and just fades away over long cable runs. But a current signal, that's more like a steady, strong hum. It's way more robust. It cuts right through all that electrical noise and stays perfectly consistent, which is exactly what you need for information you can trust.
Okay, so now that we get that, we're finally ready to solve the mystery of the 4 milliamps. And the answer is all wrapped up in this brilliant little concept known as live zero.
So here's the secret. That 4 milliamp reading doesn't just mean empty. It means empty and the system is healthy. It acts like a constant heartbeat, always confirming that the sensor has power and the wiring is intact. It is, quite literally, a built-in safety check. So let's paint a picture here. An engineer in the control room sees 4 milliamps on the screen. They think, okay, the tank's empty and the system is A-OK. But what if they see 0 milliamps? Whoa, that is not a measurement. That is a cry for help. It's an immediate red flag that something is wrong. A wire's been cut, a fuse is blown, there's a power failure. 0 is the true off switch, meaning there's no signal at all.
All right, so we've cracked the why. Now let's see how this language tells the complete story of what's happening inside a freshwater tank, from totally empty to completely full.
What's so beautiful about this system is how simple and linear it is. As that tank fills up, the current just climbs in perfect step. 4 milliamps is your baseline, empty. 20 milliamps is your maximum, full. And if you see 12 milliamps, you know without a doubt that tank is exactly 50% full. It's a clean, predictable, and super reliable code.
But this is about way more than just knowing how much water you've got. This signal is a critical, life-saving part of the ship's entire safety and alarm system.
For example, a reading around 5 milliamps isn't just a friendly heads up that the tank is almost empty. No way. This value is often programmed to trigger a very low-level trip. That's a critical, automated safety measure that can shut down equipment to prevent catastrophic damage. And of course, it works on the other end of the scale, too. A reading of around 18 milliamps isn't just, hey, we're almost full. It's designed to set off a high-level alarm, giving the crew a crucial warning that the tank is about to overflow.
So why does this matter so much? Well, that low-level trip is literally there to protect vital freshwater pumps from burning themselves out by running dry. It makes sure that water keeps flowing to critical engine cooling systems and, of course, to the crew. And that high-level alarm, it prevents a messy, wasteful, and potentially dangerous flood in the engine room. These aren't just numbers. They are the guardians of the ship and its crew.
So you see, knowing this language really transforms an engineer. You go from being someone who just reads a dial to a skilled diagnostician who can truly understand the health of the entire system.
The signal itself gives you a ton of diagnostic clues. We already know 0 milliamps means a broken circuit. But what if the reading is jumpy and unstable? That could point to a loose wire or maybe some moisture in a junction box. What if it's stuck at 4 milliamps? Sure, the tank could be empty, or the sensor itself could be shot. Even a reading above 20, like 22 milliamps, is its own special message. It's telling you there's an instrument fault. And this really gets to the core of it all. The goal isn't just to look at a number on a screen. It's to see through that number to the physical reality it represents, the actual water sloshing around in the tank, the pump that depends on it, the entire interconnected system humming along.
And ultimately, that's the key takeaway here. Understanding this secret language, connecting that tiny electrical signal to the massive mechanical reality, is what elevates a person from just reading data to truly engineering solutions. It's all about turning numbers back into knowledge,